Hi, and welcome to the Keysight AI Showcase. I'm Daniel Bogdanoff, your host for today's event. Quickly and efficiently scaling up AI infrastructure is at the top of the priority list for the world's largest companies, which is why we're seeing unprecedented investments by hyperscalers and governments and increased pressure on network architects and network equipment manufacturers. But scaling is difficult. AI data centers and traffic patterns are not like traditional data centers and require new architectures, tools, and techniques. So over the next half hour, we'll sit down with the experts to dig into these unique challenges and unveil 3 new Keysight solutions that will equip you to solve your project's toughest challenges. We'll start at the large scale, looking at the challenges the industry faces when building and running AI data centers, as well as see the new Keysight AI or Kai data center builder. Then later in the session, we'll explore brand new Keysight solutions that will help you ensure reliability and maximize performance of 1.6 terabit optics and interconnects. Finally, at the end of the event, we'll have a live Q&A session with industry experts, and we're taking your questions, so put those in the sidebar throughout the event, and then we'll bring on the experts to answer them live. We know that AI workloads are putting new demands on data centers. The stakes are higher and the timelines are shorter than they've ever been. And ensuring your data center's performance, scalability, and efficiency is mission critical. So to share more about what it takes to benchmark, validate, and optimize AI infrastructure using Kai Data Center Builder, let's hear from Ram Pirya-Krupan, Keysight's Vice President and General Manager of Network Applications and Security.
At Keysight, my role is focused on leading our next generation AI infrastructure validation, along with our network testing and cybersecurity solutions. AI workloads are transforming data centers at an unprecedented pace, and ensuring their performance, scalability, and efficiency is a complex challenge. Our team is at the forefront of AI R&D, developing advanced benchmarking, validation, and optimization solutions that help the industry navigate the rapidly evolving landscape of AI-powered infrastructure. I've had the privilege of working with some of the world's most innovative cloud and enterprise customers, helping them accelerate AI deployments, optimizing network performance, and enhancing security. I'm excited to be here today to share more about how we're helping shape the future of AI-driven data centers. Let's dive in. Large-scale AI training jobs often encounter bottlenecks, including power constraints, bandwidth inefficiencies, and component failures, each of which can severely impact the performance and scalability of AI data centers. Any inefficiencies in GPU utilization amplify these constraints. Sustained traffic implies massive data movement between GPUs, leading to possible network congestion, pushing the limits of existing data center infrastructure. Components may pass every performance pressure test and still fail at the system level, meaning that a single weak link can have a system-wide impact on AI data centers, leading to increased job completion times. The industry has recognized that these highly interconnected systems demand full-stack validation and optimization. There's a need to shift the validation to earlier phases in the design and manufacturing cycle. To help optimize the AI infrastructure, we're introducing our new architecture, Keysight AI, otherwise known as Kai. The main foundational solution of this new architecture is the Kai Data Center Builder. Kai is a suite of solutions designed to address the challenge of early validation, starting with pre-silicon, leading to devices and components, and finally system-wide qualification. The Kai architecture is focused on 4 areas: compute, interconnect, network, and power, each with a powerful portfolio of solutions. Keysight covers the full breadth of solutions across these 4 areas, covering all layers of the technology stack from physical to application, ultimately reducing the risk of workload failures and increasing AI data center operating efficiency. One of our customers, a Tier 1 cloud provider, uses the Kai Data Center Builder to benchmark network design of their new AI training cluster. They needed to make sure that their 800 gigabit Ethernet network is ready for build out and can support not only the current GPU model, but also the newer generation of GPUs which are not yet available. They were able to emulate the behavior of AI workloads specific to both types of systems and future-proof the deployment by avoiding the optimization only for the current generation. As AI-driven workloads continue to evolve, the demand for optimized, scalable, and high-performance AI infrastructure has never been greater. Power constraints, bandwidth inefficiencies, and network-level failures are challenges that AI data centers must overcome. At Keysight, we're tackling these challenges with our Kai portfolio of products and Kai Data Center Builder, which help design, validate, optimize, emulate, and benchmark AI infrastructure at scale. We're excited to partner with AI accelerator vendors, network and compute hardware providers, and hyperscale AI operators to push the boundaries of AI infrastructure. We look forward to working together to tackle the toughest challenges in AI to build the next generation of AI data centers.
Like Ram mentioned, the biggest challenges don't only affect hyperscaler architects, they impact the entire data center ecosystem, from silicon designers through networking equipment manufacturers. AI workloads bring up new challenges. The structure of AI data centers is different because of the staggering volume of east-west traffic driven by compute clusters communicating with each other. This increases network complexity and interdependence. So scaling up AI data centers brings up three major challenges. First, increasing speeds push data centers to their capacity limits, creating unexpected bottlenecks. Second, a single weak link anywhere in the network creates ripple effects, increasing tail latency, sparking workload failures, and ultimately reducing data center performance. Finally, component-level validation no longer guarantees system-level performance. Compliant components can perform poorly when put into production in an AI data center. These challenges are not hypothetical. They show up in the real world today. Expensive GPUs are sitting idle more than 50% of the time waiting on data. Idle GPUs increase training times, waste resources, and reduce the data center's ROI. And then sometimes training fails completely, causing the cluster to start over from the last checkpoint. One report shows up to a 43% failure rate. All it takes is one weak link to cause a failure. The bottom line is you need to optimize your AI data center. That means minimizing GPU downtime and pinpointing the root cause of workload failures to maximize ROI. To equip you for this challenge, we're excited to unveil today's 3 new Keysight solutions. The first is the core component of the Keysight AI, or Kai system, and it will help you comprehensively optimize your AI data center architecture. The only way to identify bottlenecks and scale capacity is by emulating real-world AI workloads. Introducing Kai Data Center Builder. Kai Data Center Builder is at the core of the ever-expanding Keysight AI system. To share more, we're joined by Allison Friedman. Over to you, Allison.
Thanks, Daniel. I'm Allison Friedman, and I'm the Product Marketing Manager for the Keysight Emulator products. The Kai Data Center Builder is a powerful software suite that helps network architects emulate anything and optimize everything, from the fabric to the application layer. This exciting product emulates real-world AI workload behavior, analyzing tail latency and network bottlenecks at scale. Through Kai Data Center Builder's graphic visualizations, you can quickly identify your longest tail latency and track individual slowdowns that cause idle processing clusters and network leaks. Imagine being able to predict and avoid fabric limitations all in one emulation system. With Kai Data Center Builder, you can. Optimizing AI infrastructure isn't easy. Data centers are inundated with torrents of traffic as they process vast amounts of data into models. Failures can occur, causing training to stop and restart, which significantly slows everything down. Tail latency, where the job that takes the longest to complete slows down the entire system, is a major issue. When performance suffers, pinpointing the root cause in a complex network environment can feel like searching for a needle in a haystack. You need clear visibility to quickly identify and resolve issues. Maximizing the use of your AI resources can be like navigating a maze in the dark. Inefficient scheduling and guessing at workload allocation lead to jobs taking too long, wasting valuable time and resources. Validating AI models can also be cumbersome, slowing down your time to market and affecting overall productivity. These challenges are what Keysight Data Center Builder helps you solve. Because when you overcome these hurdles, you unleash the true potential of your AI investments. Kai Data Center Builder directly addresses these challenges in 3 key ways. First, it emulates complex AI traffic scenarios with unmatched accuracy. This means you test your network exactly how it will be used. Second, the software helps you find network problems fast. Instead of spending days troubleshooting, our tools pinpoint issues in minutes, giving you clear insights to fix them quickly. Third, Kai Data Center Builder helps you get the most out of your AI hardware. You can test different setups without needing to buy more equipment. And you can see how tweaks to your network affect AI job times. Unlike other solutions, our product simulates the full AI communication process, the entire AI protocol stack. With Kai Data Center Builder, you can emulate anything and optimize everything, realizing the full potential of your AI technology. Back to you, Daniel.
Thank you, Allison. Quick reminder for everyone, put your questions in chat, and in a bit, we'll bring on some experts for live Q&A. So Kai Data Center Builder gives you a bird's eye view of your system and helps you emulate at scale to identify network bottlenecks and optimize your system. For the next Keysight solution we're unveiling, we're going to dive down into optical interconnects and components. It will help you validate efficiently, scale confidently, and accelerate 1.6 terabit transceiver production with fast and accurate optical testing. Introducing the new Keysight DCAM optical sampling oscilloscope. Keysight's new DCAM optical sampling oscilloscope is an essential tool for accelerating 1.6 terabit transceiver production to meet AI's demanding pace and requirements. For more, here's Ben Miller. Ben?
Thanks, Daniel. My name is Ben Miller, and I am the Product Marketing Manager for Keysight's digital and photonics test products. I'm really excited today to talk to you about the new 224 gigabit per second DCAM optical sampling oscilloscope, a powerful addition to our family of fixed configuration sampling oscilloscopes. We're launching 2 models, one with a single optical channel and one with 2 channels. With 60 gigahertz of optical bandwidth, this is the first DCAM oscilloscope designed for testing 224 gigabit per second optical data rates. It features integrated clock recovery and precision time-based capabilities, ensuring measurement accuracy by keeping jitter below 90 femtoseconds RMS and noise below 20 microwatts for a clear optical reading. This oscilloscope is specially engineered for validating 1.6T transceivers. As AI drives data centers toward 1.6T networks and beyond, transceiver manufacturers need to scale fast to keep up with market demands. For manufacturing engineers, this means designing test programs which can efficiently and accurately assist thousands of devices for optical compliance, identifying underperforming devices before they leave the production line and end up in a data center. Reliability is crucial. A single underperforming or failed interconnect could jeopardize the entire AI workload. T-Q is the key performance indicator for transceivers, but at 224 gigabits per second optical data rates, measurement margins are tight. Test programs must validate each physical lane in an optical transceiver, 8 lanes of 224 gigabit signal across temperature variations. Testing one lane or one device at a time is a slow process, often leaving hardware idle during temperature ramps. Slow or inaccurate testing increases your cost to test and delays your ability to scale production to help you meet market demands. So the real challenge here for manufacturing engineers is in designing test programs that can scale production quick enough with high enough throughput without sacrificing measurement precision and hurting your device reliability. The new 224 gigabit per second optical sampling oscilloscope helps you accelerate 1.6T transceiver production with efficient and accurate optical testing. The high optical sensitivity of DCAM sampling oscilloscopes offer the most accurate optical measurements and widest measurement margin. This ensures you can precisely characterize and tune device performance using the best TDEQ measurements. And you can use reference receiver settings for the latest IEEE 802.3 DJ standard to better test device compliance and interoperability. To maximize throughput, these oscilloscopes can be controlled by test optimization software that automates the manufacturing test process. The FlexOTO software maximizes hardware utilization and reduces idle time by allowing you to test multiple devices in parallel with a single oscilloscope, ensuring that every device is compliant and reliable. For these reasons, the 224 gigabit per second DCAM sampling oscilloscope is an essential tool for scaling 1.6T transceiver production and a key part of Kai Interconnect. Back to you, Daniel.
Thank you, Ben. And don't forget, we have the chat window open, so if you have any questions about the DCAM optical sampling oscilloscope, ask away. And while Ben just explored physical validation, that's only the first step for testing component reliability. Optical transceivers that are compliant can still fail when deployed and subjected to the types of loads we see in AI data centers. And a single failure or suboptimal component will cause performance issues. So it's important to go beyond layer 1, beyond physical layer testing. That's why we're excited to introduce the new Keysight Interconnect and Network Performance Tester. The Keysight Interconnect and Network Performance Tester is a great tool that will help you test beyond compliance with full layer 1 through 3 network emulation, so you can maximize the compatibility and reliability of every transceiver and interconnect in your network. For more, let's welcome back Allison Friedman.
Hello again, Daniel. Today, we're also unveiling the Interconnect and Network Performance Tester 1600GE and the Interconnect Test System software designed to revolutionize high-speed Ethernet testing. This powerful hardware and software solution tests reliability, stability, interoperability, and performance of 1.6T Ethernet interconnects, essential for building high-speed AI systems. Available in both benchtop and rack mount configurations, the IMPT tests everything from silicon chips and optical transceivers to cables and networking equipment at the physical, protocol, and network level for end-to-end layer 1 through 3 validation. Complementing this hardware is the Interconnect Test System, or ITS. This browser-based software is a complete and comprehensive approach to validating interconnect functionality and performance from 100GE to 1600GE. ITS streamlines testing workflows and maximizes hardware utilization. The challenges that AI data centers and manufacturers face are real. The demand for bandwidth and data throughput is exploding, driven by AI workloads and the need for faster data processing. This puts immense pressure on interconnects, which are the backbone of these high-speed networks. One component, even one that is compliant at the physical level, can still fail at a system level. So more thorough testing at multiple layers is essential for ensuring network reliability. Customers are struggling with the complexity of validating new 224 gigabits per second electrical lane interfaces, as well as the need to ensure reliability and performance at scale. Basically, they're running into a few big headaches. 1. Signal integrity. Think of it like a super fast highway. With 1.6T, the data is flying by so quickly that even tiny bumps in the road can cause a major problem. Bit error rates, forward error correction performance, link stability, and reliability are critical metrics to understand for all elements of the network. 2. Testing complexity. Testing these new connections is complicated, slow, and it's easy to miss something. You need the right tools and the right expertise to get it done. 3. Interoperability. Getting everything to work together is tough. Different parts don't always play nice. Network performance. Imagine that super fast highway. If there are any bottlenecks or accidents, everything grinds to a halt. You have to make sure the whole network can handle those 1.6T speeds without slowing down. That's where INPT and ITS come in. Together, they provide a comprehensive solution to these challenges. The INPT thoroughly tests 1.6T Ethernet interconnects to meet high-speed network requirements. Its lightweight design offers flexibility for component and system-level testing. The ITS software streamlines the process, enhancing test creation, editing, and automation. It also maximizes hardware use by allowing multiple users to run tests at the same time. To put it simply, this powerful combination of hardware and software drastically reduces testing time through automation, validates rigorously to ensure reliability and performance, ensures smooth interoperability between different components, and maximizes hardware efficiency and investment. With the Interconnect and Network Performance Tester 1600 GE and the Interconnect Test System software, you can confidently deploy high-speed network infrastructure for modern data centers and AI networks. Back to you, Daniel.
Thanks, Allison. It's about time for our live Q&A, so now is your last chance to put your questions in chat, and we're also going to pop out a survey. We'd love to hear more about what challenges you're seeing. So today, we unveiled 3 new Keysight solutions. Kai Data Center Builder that helps you scale your AI data center capacity. By emulating real-world workflows and identifying bottlenecks, you can emulate anything and optimize everything. We saw the new DCAM optical sampling oscilloscope that will help you ramp your 1.6 terabit optical transceiver production. And we looked at the new Interconnect and Network Performance Tester that helps you validate on multiple layers. These are all part of the Keysight AI or Kai architecture. Kai solutions scale capacity in AI data centers by validating individual network components and using real-world AI workload emulations to optimize system-level interoperability, performance, and efficiency. The Kai architecture has 4 main pillars. Kai Compute helps semiconductor and digital designers pioneer next-gen AI chip development with intelligent physical layer design and validation. Kai Interconnect enhances AI data center capacity and connectivity with advanced photonics research and transceiver validation. Kai Network validates AI data center network performance with collective communication and synthesized AI workloads. And Kai Power scales AI workload capacity by improving power integrity and data center components. And now it's time for our live Q&A with experts. I'm joined virtually and live by 3 of our Keysight experts. We have Alex Bortok, lead product manager for Kai Data Center Builder. We have Charles Seifert, senior manager of product management, and Ahmad El Chayeb, planner for optical solutions and Data Center Connect. Thank you all for being here. Let's go ahead and get started with some live Q&A. And we got the chat here, so feel free to put your questions in chat, and we'll ask them to these folks. Alex, we'll start with you. Can you tell me a little bit about tail latency in AI workloads? How important is it to identify and manage tail latency? And are there any real-world examples where you've seen people be successful mitigating that issue?
All right. Thank you for the question. Well, the latency really defines for how long the overall GPU cluster gonna wait for the data movement to finish, even if there are some movements of data that finish much faster. If there are laggards, everyone's going to be waiting for them, and that's what tail latency really measures: is how much is the difference between the fastest and the slowest. And there are different reasons for that tail latency to be out there. One of the examples I can give is congestion control in Rocky V2. Which is called DCQCN, if you love these abbreviations. But that congestion control, depending on how well it is tuned for your workload and your topology, it might introduce a huge variation of the bandwidth for each individual queue pair, which is sort of a connection in the world of AI data movement. And if you don't fine-tune it properly, you're going to see all those variations. And we have real-world examples where people use Kai Data Center Builder to find out the optimal settings for their topology, for their network, and for their workload, and thus reduce that to very small variations.
Wonderful. Thank you. Can you tell me about 1.6T physical layer testing with the sampling oscilloscope? How does thoroughly testing your devices help improve network reliability?
Thank you very much, Daniel. This is actually an excellent question. So reliability, resilience, interoperability are key requirements for optical interconnects in the data center. Typically, in an optical link, you will have a transmitter, a channel, which is the fiber, and a receiver. The primary objective for the N1093 optical sampling scope, which has 60 gigahertz of optical bandwidth and 120 gigabaud integrated clock recovery, is to test the transmitter in this link. So the key metrics for characterizing the performance of a transmitter on an optical TX lane are typically TDEQ, transmitter dispersion eye closure quaternary, CEQ, outer OMA, optical modulation amplitude, extinction ratio, and RIN OMA, the relative intensity noise. So these are the typical measurements that you do on an N1093. And with the bandwidth of the N1093 and the integrated clock recovery, it is, as far as I know, the only tool on the market that can do these measurements compliant to the IEEE 802.3DJ specs. So in this way, you can ensure your transceiver reliability, resilience, and interoperability.
Wonderful. Following up on that, does this also do linear drive or linear pluggable optics at 200 gig lane speeds?
That's an excellent question. And quite honestly, this could be a webinar on its own. It's a very long subject, but let's try to answer that. So the exponential growth of compute cluster size within the data center is fueling an insatiable need for optical interconnect. The typical classical retimed module, 50% or more of the power consumed by a classical retimed module is actually consumed by the DSP. So the sheer number of retimed modules being deployed into the data center means that the power requirements are going crazy. And this is why there is a huge drive to drive linear pluggable optics. So LPOs, linear pluggable optics, and RTLRs, retimed transmitter linear receiver. The short answer to the question is yes, but let me try to elaborate a little bit. So again, as I said, there's two main classes of LPOs and LROs. I'll start with RTLRs, also called LROs or half retimed modules. This type of linear pluggable optics will have a retimer on the transmitter side. So at least on the transmitter, it's exactly the same as a retimed module. So we do the same kind of testing on the transmitter side. In this case, the linear portion is the receiver side, which requires different testing. For the LPOs, the linear pluggable optics, these are completely linear modules, and they do not have a retimer. So that means the input signal to the T-ROSA, the transmitter receiver optical subassembly, is actually an impaired signal, which makes testing these signals a bit more challenging. However, the methodology for the test is still pretty much the same. So it relies on the same metrics, TDEQ, CEQ, OMA, extinction ratio, and RIN OMA. The parameters and the allowances for these metrics are different depending on which spec you follow. So there's two classes of specs. There's the OIF, EEI, and CEI 112 gig linear specs and 224 gig linear specs. And then we have the LPO MSA, which is an MSA form to redefine the optics for these linear pluggables. So depending on which spec you're following, the requirements or the allowances might change a bit, but the test methodology is the same. And the N1093 DCAM is still the primary tool to do these measurements.
Wonderful. We did get a question around from Amarjit about Data Center Builder. They're asking if there's an eval version or a training available for the Data Center Builder. Alex, how can people learn more about this and kind of get their hands dirty with this if they want to try it out themselves?
Right. We actually do support ability for customers to evaluate the product. So they could go to the Kai Data Center Builder product page on keysight.com. And let's paste that into the chat one more time. I think I did that once. And then there is a button there saying request demo. So just click it and we'll get in touch with you and schedule a demo and
Wonderful.
the evaluation. Mm-hmm.
Great. Yeah, we will get that link back in chat. That was in the Q&A field for everybody out there. Mm-hmm. Thank you, Allison, for putting that in there. We've seen a lot of traction around and a lot of strong interest in the Data Center Builder program. So, Alex, I got another question coming for you for that. Can you talk about how we're actually, so we've talked about how it emulates real world workloads, but we haven't touched how we're actually generating that traffic at scale. Can you talk through what does it look like to actually generate data center style traffic at scale, and what does it take to do that?
Yeah, that's right. So when you have a workload, which is kind of a signature of what the real AI training or inference job would be doing, the objective for us now is to replay that essentially on the infrastructure that you have, so that maybe you would try to fine-tune certain parameters or try different topologies or something, right? There's a lot of kind of options that you have to define how the AI data center should look like. And so for you to be able to replay, we offer two options. The kind of straightforward one is that you can get a traffic generator from Keysight, which is a high-density specialized appliance with a bunch of high-speed interfaces that you just plug into your fabric, and thus you can use that to replay the workload through your network fabric and see how the fabric performs. As the moment you feel like your fabric is solid, and what you could also do is then replay the same workload on a bunch of servers, which, by the way, don't need to have GPUs, because we kind of emulate GPUs in that regard. And so instead, you could use a lot of servers to test how the actual network cards you're going to be using how their configuration gonna align with the network, and thus sort of continue your fine tuning. And that mode is also very applicable to customers who wants to understand the performance limitations in the cloud data centers where they rent GPUs from one of the neo clouds, right? You cannot plug in our traffic generators to those setups, and so yeah, that's the option that is popular between among those customers.
Wonderful. Charles, the next question's for you. What sort of metrics do you look for, and what sort of metrics are people looking for when they are testing interconnect and network performance?
Well, what we want to start with is really qualifying the reliability of the interconnect itself, whether it's an optical transceiver, an active copper cable, or a passive copper cable, which are the most common types. And what we want to measure is the BER, the bit error ratio of the device's performance on each of the electrical lanes that we've talked about before. And also, what is the forward error correction performance? How well does it correct the inherent errors that are in these high-speed signals? We can't get rid of them all. So how well does it correct for those when it's being operated in a way in our test tool, the Interconnect and Network Performance Tester, it's being tested as if it's going to be used in a real production network. So we want to determine what is its error correction performance.
So what sort of steps are being taken? What sort of measurements are being made to actually fully ensure thorough validation?
Well, there's an important measurement called pre-FEC BER. So that's involved, it involves itself in creating a bit error ratio, again. However, it's based on the FEC performance. And that particular number has a lot to do with how the FEC symbol error correction performance actually works. So we have a measurement called symbol error distribution analysis. And you might say, oh my gosh, this is a complicated thing. But what it does, it determines what we call the FEC overhead, which is how many errors are actually occurring, versus the FEC margin, which is how much error headroom do I have on this device before it will fail. So by doing FEC symbol error correction distribution analysis, we can predict when the device may fail. And forward error correction also creates, in addition to the burstiness of network traffic by itself, it also creates its own bursty errors, which means bit errors just fly in and fly out randomly. We can never predict when they will come. We will never predict when they will go, but they just come and go. And because of that, with our symbol error distribution analysis, we can detect when they happen. And so the end user, the final customer, wants to know, well, even if in the presence of bursty errors, do I have enough error margin so that I will not drop a packet? I will not drop any data. I won't have to do a retransmission of data because of the failure, or let's say the lack of error correction performance of the device. So I hope that answers your question.
I think it does. How does understanding your margins and operating within these sorts of design parameters impact your overall end product reliability? What gives people confidence that it's going to work when they plug it in and get rolling?
Well, the IEEE, for example, and the OIF have set standards with thresholds. And we talked about some of those measurements earlier at the physical layer that Ahmad talked about. And when we move up to what we call the digital layer, when we're sending bits and bytes, right, zeros and ones, right, not only the analog signal or the optical signal, now we're talking about the digital signal. So we now have established, let's call it practices, where there are certain thresholds that are the maximum allowed for interoperability, meaning multiple devices working together, a switch, a router, a server, a NIC card in a server with a switch, whatever devices are connected together, there's a certain amount of error that can occur before that interoperability fails. Now, that's the worst case errors that defined by the standards. Most customers want optimization, and they want much better performance than is what's defined as the maximum error for operation by the standards, because the standards want everybody to play. But when everybody plays, we want better performance than the worst case. So we want, the optimized case. We want the best case we can get for our interconnect, and that's what we help people measure. And depending upon the application, or let's say the Ethernet speeds they're running over the interconnect, there's all the different kinds of Ethernet speeds on a per port basis that are operated. Depending upon that, we take a look at the FEC margin. How far away in the amount of error am I from an actual uncorrectable FEC code word, which creates a lost packet in the network? How far away am I from that? And we help people judge that distance. that accommodates the bursty errors, that accommodates the remote possibility of a lost packet. Right? So that's kind of how we help people build that confidence that I have enough error margin that I feel that if I put this into my network and I've stress test this device enough, that it won't fail. And when I have hundreds of thousands of these installed in my network, possibly millions, and I have spent more money on the optical transceivers or the interconnects than I might have spent on the actual equipment they run in. So that's a real dilemma that people face. And so with that kind of investment, you really want to know, do I have that margin for error? And can I predict that? And our test tools help people predict that exact same thing.
Absolutely. And I think the idea of just because it passes spec doesn't mean it's as good as it could be, where having a better connector is a competitive advantage and it gives you better performance in the system. And who doesn't want that? From there, let's go ahead and talk a little bit more about the DCAM sampling oscilloscope. And Ahmed, what sort of trends are you seeing in the world of testing optics? And what sort of challenges are people running into that are new for these speeds and new for this sort of data center environment that we're seeing today?
So actually, with the move from 100 gig per lane to 200 gig per lane, the margins are now much, much tighter. And so that means a couple of things. One, you require a scope that has an integrated clock recovery. There was other methods that were being used, like a half rate clock on an adjacent lane. This method, one, is not compliant, and two, when you don't have a clock recovery, your clock recovery typically tracks out the sub loop bandwidth wander jitter, and in that case, your jitter numbers might be higher. The other one is the contribution of the DCA channel that you use to your TDQ measurement. TDQ measurement is a penalty-based measurement, and essentially what it does, it's an estimate of what's the penalty on the receiver input for the non-ideal performance of your transmitter. So what that translates to is you're adding noise mathematically to the waveform in order to find out what's the penalty compared to an ideal reference transmitter. Now, the noise in your system comes from two different sources. One of them is your DUT, and that's the noise that you want to measure and characterize. And the other one comes from the scope itself. So every instrument will have a noise contribution to the measurement. And the lower the noise measurement floor for that instrument, the more margin you have. This is becoming essential and critical in today's 200 gig per lane optics.
Interesting. Yeah. So definitely some new challenges with those margins shrinking.
Yes.
Thank you for that. Yeah. We got another question from the chat. Another data center builder question from Vijay. The question is, Alex, for you, does Kai Data Center Builder support creating congestion to fine-tune customers' infrastructure support for PFC, ECN, DC, QCN?
Right. So the congestion happens sort of by itself when we run collective operations, because just by nature of them, you would have some overlap of different data streams coming to a single destination. So, and that's what we want. We don't want contrived congestion scenarios. We want congestion scenarios that represent the realistic situation as close as possible. And because that happens, that realistic congestion is essentially what Kai Data Center Builder allows you to recreate. The fine-tuning of all the parameters like PFC and ECN thresholds, as well as the DCQCN parameters, becomes not a theoretical exercise, but an actual practical one, which would be helpful for your specific workload to perform the best. Right. So that's the essence of why we build the Kai Data Center Builder. We essentially want you to we want to give you a tool that creates as much realism as possible, so that fine-tuning of those parameters would be meaningful to your workload.
Wonderful. Maurice in France also put in chat, this is another question for you, Alex. You mentioned GPUs and maybe even not needing GPUs. Can you talk about the role of how FPGAs and how we're actually able to do some FPGA-based work to emulate these sorts of workloads at scale without requiring like real live GPUs in our lab or in our systems?
Right. Right. Well, so the difference here is, I mentioned before that we have two options for actually generate traffic. We either use a traffic generator or we can run on real servers. So when we run on real servers, we rely on the network card to be able to send data. We talk to the network card the same way as the GPU would. So in that sense, the GPU is kind of a client. It tells the network card, hey, I have a data here, just take it and send it over. So we are emulating GPU in that regard, and thus asking the network card to move the bytes. Right now, when we are having a traffic generator, essentially what we enable you to do is to emulate the whole server with all the network cards. So, and why is that helpful? For a variety of reasons, is when, for example, let's say you want to understand how can you build the next generation of the network, let's say for 800 gig and quite soon for 1.6T speeds, and you don't have network cards yet, right? So you're waiting for the next generation of GPU-based systems to come in, which would have those cards, but you don't have them yet, but you have a network already. So you would use traffic generator to validate that your network is ready. And the traffic generator has FPGAs inside. That's kind of a technical detail. So we use FPGAs to emulate those high-speed network cards with all the congestion control and other parameters in the Rocky V2 protocol. And thus, and so that's one side. And then the other side is, by us being able to emulate the network cards, we can actually quickly fine-tune all sorts of parameters that those network cards expose to the user. Very often, changing any of those parameters sometimes even require to reboot a real server. With a traffic generator, you don't have to do it. You can iterate much faster and then figure out what's the best setup or combination of parameters that works for you.
That makes a lot of sense to me, that like if you're waiting for your GPUs, as soon as they show up, you want to put those things to work. So having a network that is ready for the GPUs to pop in makes a lot of sense, and being able to plan ahead and also not run them on your actual GPUs, so you can use them for the actual work you are hoping for those GPUs to do. So that makes a lot of sense. Thanks, Alex. Another question for Ahmed: what is the driver to test TDEC-Q versus a system level check using a bit error ratio test?
That's an excellent question. Actually, there's a lot of discussion in the industry going on if we need to do a TDEC-Q measurement versus just doing a bit error ratio test or BER test. And my answer is yes, we absolutely need to have TDEC-Q for the following reasons. So TDEC-Q is a transmitter metric. Again, it's transmitter dispersion eye closure quaternary. A BER measurement is a system level measurement, which requires having a transmitter and a receiver at the same time. Without having a receiver, a transmitter on its own does not do bit errors, right? So a system level test ensures that that specific transmitter operates with that specific receiver in that link. However, it does not ensure interoperability. So not all receivers are created equal. And by testing the transmitter dispersion eye closure quaternary, TDEC-Q, you are saying this transmitter will interoperate with any compliant receiver without differentiating that particular receiver in that link. So if you have a closed system, you can get by with the BER test, but in the data center, where you have multiple vendors and you have an interoperability ecosystem, you absolutely need to test CEQ, TDEC-Q, OMA extension ratio, and RIN OMA.
So the testing requirements are higher, and really you want to make sure not just that it works in your lab in the controlled environment, but that when you plug it into a data center, literally it's actually going to work regardless of whatever receivers are out there.
That is correct. I mean, in a data center, you have multiple vendors and they're selling different parts, switches, transceivers, fibers, transmitters, receivers. It's not enough for you to make sure that your transmitter interoperates with itself, as in looping back a traffic from your transmitter to your own receiver and verifying that. You need to make sure that transmitter will work in the field with any compliant receiver.
Absolutely. If people wanted to learn more about this DCAM and they wanted to potentially try it for themselves, poke in a little more, where would you recommend people go to find out more about this thing?
Well, I would absolutely recommend you get in touch with your local Keysight team. We do have demo systems for the DCAMs, so we can arrange for the N1093 demo unit. We also have demo license keys if you want to do these advanced measurements such as TDQ and RIN OMA. But for the hardware, absolutely get in touch with your local Keysight team and they will get us involved. And we're happy to talk to you more in detail about the DCAM and the measurement science that makes all this possible.
Wonderful. It is some spectacular measurement science. I love this stuff. And also, we put another link in. If you want a demo for the Kai Data Center Builder, there's a link for that in chat as well. But we are out of time for today, so thank you all for tuning in. If you have any questions or you want to learn more about this, go to keysight.com/find/KeysightAI. And on behalf of the whole Keysight team, thank you for joining today. That's it for our stream, but we'll see you for the next one.